Hi, I'm Dr. Sapri. Assalamualaikum and good day. I'm going to teach on the chemical reaction engineering, one of the topics under the introduction to chemical engineering. At the end of this lecture, I hope that you are able to describe concept of chemical reaction chemistry, and after that to explain reaction kinetics, how the rate law, the equation that we use to express the reaction kinetics and how it is used. And finally, to explain the technology of basic reactors to conduct the chemical reaction. How we can identify the uh, reaction. It starts from the change of the identity of chemical. Chemical can be identified based on the first is a kind of the chemical. For example, under hydrocarbon we will call alkane, alkene, aldehyde, alcohol, and so on and so forth. And from the same group, maybe we have different number of atom, particular carbon. So change of number of carbon also will change the identity of a chemical. And finally, if you have the same kind, same number of atoms, probably you can also have different configuration of molecules. So we call it isomer. For example, here we have alkane. The kind of chemical is alkene, sorry, and the number of carbon is 4, which is under the name is butene, and the location of double bond would be also indicated different number of the number in the name. As you can see, name 2 here is reflecting the carbon number 2 will have double bond here. The location of the metal on the carbon will also be different. As you can see, a cis is at the same side. Yeah, will have more positive. Here will be more negative. And so because of this, it will be more polar compared to this configuration. And the boiling point for cis butene will be more, although the number, the type of chemical is same, number of carbon is same, the configuration is different, so the chemical is also different. If there is a reaction that change from cis to trans, although the chemical is the same kind, the same number, but because of different configuration, we also consider this as chemical reaction. Because of the change in kind, change in the number of atoms, and change of configuration, so we can define reaction as detectable number of molecules of one or more species lost the identification in terms of chemistry and new compound forms. So because of that, you will have a decomposition, for example, from A. Assume we have A, then it will become B and C, for example. And then we can also have combination. If we have, like, say, A plus B to form C, so it will be the combination. It can also be isomerization. The same, the molecule will change to a new isomer. So there will be just only one molecule, and then one type of chemicals, and change to the another chemical with the same kind and the same number of atoms. Consider a reaction like this. There will be two reactants here, chlorobenzene, and two products, which is DDT, water. The formula structure of each component will be this, and this. As you have learned probably in the chemistry, you have to balance the number of carbon and the number in front of the molecule structure, or formula will be the stoichiometric coefficient. So in reaction engineering, normally we will symbolize uh, species into A, B, C, D, so on and so forth to simplify the reaction. Normally, A is for limiting reactant, and B is for the excess reactant. We can identify excess or limiting based on uh, stoichiometry, stoichiometry, stoichiometric ratio, and we need to have another information with this, which is feed ratio. For example, in the reactor, we add like here we have, for example, in the reactor we have 3 chlorine and 1 chlorobenzene. So definitely, sorry, for example, we have, for example, 1 chlorine, 1 mole chlorine, and 3 mole of chlorobenzene. So definitely we'll have we'll finish chlorine first before CB before CB. So that means chlorine will be limiting reactant for reaction to occur. So we can symbolize chlorine as the limiting reactant. That's the way in chemical engineering normally to symbolize the species. In chemical reaction, we have the parameter to design and to make sure that the reaction occurs in the specific time and with the desired conversion. We introduce here the rate symbol as negative RA. R is the rate, A subscript A is number of is the chemicals that this rate referring to. So RA is the number of moles reacting per unit time per unit volume. It can be more per liter per second. It is positive or negative. Next is another symbol for the rate is RA prime, which is the number of moles per unit time per unit catalyst, or mole per second per gram catalyst. Or we can also write the other way around, which is mole per gram catalyst per second. The rate like is somewhat like a vector unit, which is having direction. For example, here we have positive, meaning it is a formation. Normally, it is for product. And then we also have negative, which is transformation or consumption. It is normally for reactant. It is for reactant. It is for product. Product will be positive because it will appear and the number of mole will be decrease for the and then but the reaction will decrease, so it will be negative. Assume we have this example. Initially we have 3 mole Fa, and assuming we have a very simple reaction, isomerization from A to form B. This isomerization, change of molecule configuration. Initially we have 3 mole of A, and then occur like 1 mole of A where 1 mole B formed from the A. So how much A missing from the initial condition? So initially you have 3 mole of A in 1 liter beaker, reacts as the condition. After a minute, 1 mole B is being formed. Based on this stoichiometry, if 1 mole B appeared, there is just only one reaction. That means 1 mole A has missed, has been used. So apparently that the apparent rate of formation of B is Rb equals to 1 mole per liter per minute, because it is 1 mole, 1 liter. So 1 mole B formed in 1 liter of beaker in 1 minute. So apparently the rate can be written as 1 mole per liter per minute. and then A will be negative RA equals to 1 mole per liter per minute. Negative RA, negative because it is consumption. However, the rate is not directly proportional to time. So after 1 minute, the second minute will be no longer one mole of consumption. Will be slower. It will be slower. So the second minute will be lesser mole. For another, so here will be not higher than 1 minute. Here will be 1 minute. So the next will be longer than 1 minute. So if you plot a graph, we have plot, for example, like this. It will be the graph like this. So initially we have 3 mole of A, and then drop to 2 mole of A after 1 minute. At the same time, B also formed. So this black dot and line is for B. After about 1 and I think from 2 to become 1, it will be 1.5 minutes. 1.5 minutes. As you can see here, this is 1. So the time here taken to achieve 1 mole of A is about 1.5 minutes. So it's no longer 1 minute. So this is an example of reaction for acceleration from A to B. So we calculate the rate at 2 here as 1 per mole per liter, 1 per mole per minute, 1 mole per liter per second, per minute, sorry. And actually, when we calculate the slope of this line, it will be 0.85 mole per liter per minute, not 1 mole per liter per minute, not because of the method, but how we analyze. The way we analyze is by plotting the graph and find out the slope. Similarly, for rate 2, it will be lesser. So if we use this method, you can find the height and the length of this triangle so that we can find the rate, right? So this is the value of y-axis, this value of axis, so that you can find the slope or the gradient. So from there you can find the rate. So the rate will be the first part here will be 0.85 mole per liter per minute, and this one you can find out yourself lah. When you plot a graph, open, we use a log graph. So we find out the rate from the previous graph, and we plot again with the ln C, the concentration of A. When we plot the graph, ln rate versus ln concentration of A will have a straight line like this. And by using the Excel regression or fitting the curve by introducing the trend line and then check the equation of the trend line, you can have this equation. What does it mean? We convert into equation, it will be ln negative RA equals to 0.9898 ln CA plus ln 0.428. We convert into power quotient, it will be negative RA equals to 0.428 CA to the power of 1. We round up this value into 1. What does it mean? This equation is the rate law determined via graphical method. 0.428 is rate constant and 1 is the order of the rate law. We call this power law model. One of the model used to capture the progress of the reaction is power law model, power equation. And this is going to be the rate law for your syllabus. In math, we can also determine the constant power for this equation using numerical method. There are a number of method in mathematics to find out the constant and power. In Series 1, in chemical reaction engineering, you will learn how to formulate the rate law using several methods, including this one. But it's not going to be not this one is not for your level. Sorry. Next is on the K. This is going to be value of K, and here is 0.28, 0.428. What is K actually? K is called as Arrhenius constant. Sorry, the rate constant. We determine the rate constant from the temperature. This is equation of Arrhenius equation to determine the rate constant. If we have two conditions like this, we can come up this equation. Initially, it's T0. At T, you can find what is the rate constant if the activation energy is given, temperature, both temperature is given. The A will be cancelled out, and then it will produce this Arrhenius equation. These are rate constant. The Arrhenius equation will have activation energy. Reaction on of activation energy will be the energy at this stage. If you use catalyst, this activation energy will be lower. And temperature is important to reduce this to let the reactant overcome the energy barrier, so that the contact is effective to let the reaction to occur. And normally, if you plot a rate constant versus absolute temperature, it will be sigmoid graph like this. And normally we plot K ln K versus 1 over T. We will have a straight line. We'll have straight line. Okay, this one lah. Okay, sorry, we will have straight line like this, where the slope will be an activation energy per gas constant, and the intercept will be ln A, which is the Arrhenius constant, or the frequency factor, because you can also frequency factor. Next is on the power law model. If you have one reactant, the power equation will be negative RA equals to KCA to the power of alpha. If alpha accidentally from the experiment same as A, that means the reaction is elementary. Elementary means I give you this reaction, you can write straight away the rate law. The power will be similar to the stoichiometric coefficient. If not, we call the reaction as non-elementary. Similarly for the others. And if you have two reactants, the power law or power equation that you have to write is this. This is irreversible. Irreversible. The power is alpha for A and beta for B. If accidentally alpha and B respectively same as its stoichiometric coefficient in the reaction is called elementary. If not, it is non-elementary. This is irreversible. What happens if we have reversible? You will have reverse reaction. So this is a reverse reaction if you want to write the rate law based on the power equation. So negative R equals to KCA bracket A to the power of alpha minus CB to beta per Q capital K E, where K equals to the ratio of the concentration of B and concentration of A with the power respectively. And also we can calculate the KE, which is the equilibrium constant from a ratio of rate constant, forward reaction, and reverse reaction. And again, if alpha and beta symmetric, the stoichiometric coefficient duration is called elementary. If we have more species in the reactor, you have a larger, more variable in the rate law. And again, if the power same as the stoichiometric coefficient, the reaction is called elementary. Relationship between rate and reactions in the reaction. How we normally calculate the rate law for negative RA. So how do we find a rate for other species in the reaction? Based on the stoichiometry, this correlation or relationship will be used. So let's say if you want to find out what is the rate of V, you can use this equation. So on the rate law of A, RB will be negative V per negative A and then RA like that lah. Okay. Example, if you have, for example, 2NO plus oxygen to form 2 nitrous oxide, so you have this correlation. In a study, reaction kinetics are formulated based on experimental rather than simply to suggest it with specific number. It is not from your mind. It's not from the way you write the reaction. It is coming from the reaction. You are going to use power equation. If you have this reaction and the stoichiometric coefficient of A here is 1, and the rate law from the experiment you get it is negative R equals to KCA to the power of 1. So this is elementary. But if you have powers of 2 for CA, this no longer is elementary. So you can have also this rate law for this reaction. Other than the power equation, you can also have other model of equation. For example, in this example of Langmuir-Hinshelwood. There will be number of models used to express the reaction kinetics for reactor design. So this is called Langmuir-Hinshelwood. Next, I would like to so now you have get the idea what is the rate of reaction, starting from the reaction, and then what is the rate of reaction. So there are so many phenomena happen around us. Which one of the phenomena will be reaction, chemical reaction, or what are just phenomenological occurrence, not a chemical reaction? So you have so there are 3 things that you have to consider, which is the change of chemical identity, which are a kind, a number of atom, and then configuration. And after that, I have taught you on how what is the rate and how we actually calculate the rate from the experimental data. Finally, I would like to introduce the type of the reactor normally used to conduct the chemical reaction. We have batch reactor, we have continuous reactor. Under continuous, it will be also tank. This picture illustrate the tank type, but it will have piping for feed and piping for product. So the flow of feed and product will be flowing continuously. Apart from this tank, you can also have tubular type of reactor called a plug flow reactor. Plug flow reactor doesn't have any packing inside, whereas fixed bed reactor and packed bed reactor will have packing inside, packing of catalysts and others. The size can be bench or in the lab, in the laboratory, on the bench, or the pilot, and industrial scale. Pilot scale is uh, the sign in between of lab scale and the industrial scale, normally used to uh, study the mass transfer and hydrodynamic of the flow system. That's all for now, and we'll go to the next subject, which is the reactor. Thank you.